Welcome everyone to today's webinar, LiDAR and Photogrammetry, the tools behind accurate 3D models, presented by Skyline Software Systems Director, Production Sales and Services, Ben Schechter. My name is Catherine Ryan and I will be your host today. We are aiming for about 20 to 25 minutes of content as well as some time for questions at the end. Please submit your questions using the questions area on your GoToWebinar screen, and Itai will be happy to answer at the end. Also, everyone who registered for today's webinar will receive an email with a link to view a video of today's presentation. The webinar video will also be posted on our website, www.skylinesoft.com/events, and on our YouTube channel. So let's get started. Itai, thanks so much for being here, and I will go ahead and turn it over to you.
Oh, thank you so much. So today we will be reviewing some of the capabilities inside Skyline's PhotoMesh software on the both workflow and features that are available, as well as some recommended guidelines for how to use it, or some best practices, some rules of thumb regarding the data and the best way to work both of them together. So I'll jump right in and we can go over, I prepared two projects that are from different systems with slightly different resolutions, LiDAR density, and types of areas. And we could see how we process them through PhotoMesh. So we'll start with the first one. So this one will provide credit for Blue Sky, which is one of our large customers in the UK and our Skyline UK offices. So this data was collected with a Leica City Mapper. Here you're seeing all of the data loaded at once, and we'll sort of break it down. So the icons that we're looking at are the 5 camera systems, which is a nadir and then 4 oblique cameras. PhotoMesh has the ability to import the data in with the raw airborne GPS IMU information, and then perform the entire aerial triangulation process and everything that's necessary to get the images to align to one another, as well as align to the LiDAR if it's necessary to co-register the 2 data sets using some control points. Here you're seeing one of the collections, and we can double click on one of the images, see which image it is. There's the image, and here's the input position, omega phi kappa, and also any coordinate system we can work with that is a standard coordinate system. So you can see over here we support really any EPSG or any vertical datum that the data comes in and that the data can be exported to. So as part of the process, we perform the AT, as I mentioned, and we can look at an AT result of this specific project. We could process unlimited amount of images in a single project. So that could be, we've processed projects up to almost 950,000 images. We have the ability to divide the data into AT blocks and then merge those AT blocks together. That all gets done automatically, and each AT block can be close to 10,000 images or more, depending on good hardware. So we look at the AT report here. We see the general residual was below 0.3 pixels, slightly above 1/4 of a pixel, which is very good. Here we're seeing the control points that were used from the LiDAR in the report. We see they all have very low residual, which means that the registration worked very well. And here we're seeing we also do in situ calibration. So we recalibrate the camera models based on observations in the AT process, the aerial triangulation process. And usually if the camera is a pretty metric camera, the differences will be very minor. As we see here, the shift is from 5168 to 5169, so it's about a 1 pixel shift in the principal point, or 68 to 70, 68 to 77. So the shifts are very minor, which tells us that it's a pretty good sensor, as well as the changes in the focal length. The radial distortions are also considered very low. But it's still critical to go through the calibration process just to be able to get a very low residual, very low median error, which then allows to produce a high quality mesh model from the data, even if it's just from the images, but also to make sure that the LiDAR, which is very geometric, matches the image-based point cloud. So we look at one of the control points, and we can just randomly jump to one of the control points that was used. Let me turn it on. And we can also display the LiDAR file. Here's the LAS file, and we can show it on the terrain and visually see it inside PhotoMesh. So we could see the LiDAR being displayed with the intensity. This is a pretty good LiDAR. I'd say the density is probably around 20 points per square meter. The point that was selected here, and you can see it's usually better. So this is some of the rules of thumb or guidelines for how to pick control from the LiDAR. You don't want it to be close to a very tall building, like on the ground here, because it will be obstructed by the oblique views from the different angles. So you will only be able to see it, let's say, from the nadir camera or from only one or two of the obliques. You want to pick something that is in a relatively open area without many obstructions around it, so that it could be seen from all the different image combinations. And then it can be properly referenced to the nadir camera as well as the several oblique cameras. So as you zoom in, you can see it's hard to discern the points. They become a little sparse in the view. So we have different options for how to display the points. I can make them a little bit thicker, and then it's easier to see the features. Now, to people that are familiar with the road markings in England, they have sort of a zigzag line right before crosswalks and generally on the road. And over here, there's a corner that represents the end of this line and the end of this line that meet right here in the edge. So let's pick this point and visualize. And the way to do that is you can just go over here to create ground control point from terrain, and then pick the feature that you want to sample in the LiDAR. It provides the feature with its exact coordinate X, Y, and Z from the LiDAR, wherever it was picked. And then that point can be sampled inside the images. So we'll load our control point editor. Now, our control point editor allows, it automatically selects which images appear in the point, in the coordinate. And then those images should be pretty close. Let's say with this data set, they're probably already within half a meter or less. Obviously, for good referencing and high quality output, you want them to be within a couple of centimeters. So this is what this process does, is it allows you to pick the control points from the images and visualize them. Now you see in our control point editor, we have a very flexible filter or list. So what we're showing is all inside PhotoMesh. This is all Skyline's PhotoMesh 3D software, 3D textured mesh and ortho and DSM and point cloud creation. You can see with the filtering tool, I could pick either one of the collections, and this one's the nadir, and then these are the 4 obliques. So I can filter and let's say view just the nadir, or I can sort based on distance and see the nadir is going to be the closest. So if we look at the nadir image that was picked, this is the image, and here is the edge of the line, the corner of the line that was used to reference to that same feature in the LiDAR. You can see that there's movements in the shadow, there's time differences. This also helps align things to the LiDAR and help the images overcome some of that when they go through the point cloud generation, the dense point cloud extraction. We can see this is an oblique image, as you can see, based on the view of the buildings from the side and viewing the building facades. And the same point gets referenced in also those images. As a good rule of thumb, it's recommended to pick at least 4 or 5 images from each perspective to make sure you have a couple of stereo relationships. And that way you make sure that you're referencing each one of the cameras, the left-looking camera, the right-looking camera, the forward and the back, as well as the nadir, all to the same point with very low residual. So that's how the control point process works. The number of control points, which is a very common question, it really depends on the size of the projects. The recommended minimum is about 4 or 5 per AT tile, so that the AT, the aerial triangulation, goes through a proper bundle block adjustment and is able to reference the entire data set. If there is a water body, like in this case, the Thames River, sometimes the images on the sides of the river, depending on how wide it is, don't necessarily get perfectly matched because match points in water are not that high quality. Water does not have a lot of static features. So it is recommended to treat the north side, let's say, and the south side as separate blocks. So I put about 4 or 5 on the bottom, on the south side of the project, and another 4 or 5 on the top side of the project. So once the aerial triangulation gets done, the process then moves on, and let me turn off the LiDAR tiles so they don't get in the way. I can also turn off the images so that we can see just the reconstruction step. So these are all the reconstruction tiles. Now, PhotoMesh has the capability to split up the project into separate tiles, and then each tile and then run a different project. And over here in a production, we have about 75 machines that are available for processing. You can also do this on the cloud or bring in AWS instances and really run an unlimited amount of CPUs and computers. And I think the most we ran was on about 500 machines in parallel. So each one of the processes goes through, each one of the tiles goes through the process of generating a dense point cloud, which is every visible correlated points from at least 2 images or 3 images, really any sort of combination. And we can see what the dense point cloud looks like. So this is one of the dense point clouds in the areas, and all of the features that it was able to correlate from the different oblique images. The mesh model is the geometric surface that gets generated from the images, which is a full 3D surface. So whatever is being able to viewed underneath, which LiDAR a lot of time does with vegetation. So trees will be correlated below the tree using the LiDAR points. As you can see in this example, the area over here was not correlated from the images. It was supplemented from the LiDAR points. And then the textured model, which we can see of a single tile. And then we automatically stitch all of the tiles together, so they produce one comprehensive mesh model. And this is an example of a small area of tiles. And you can see you'll not be able to see any sort of artifacts or any sort of seam lines between the tiles. They get integrated seamlessly. And over here we can see some of the ability of the images to still texture the area underneath the tree. So it's a combination of the LiDAR geometry and the texture from the images, which might not have been able to correlate a point, but we calculate the normals from the images and we're able to then bring in texture into this area very tight under the tree. We also do very smart interpolation. So when there's no data, there isn't just a blank gray space or black space. And the images then get interpolated using the available texture and is able to produce the combined output. So At the end of the process, everything gets stitched together into a single 3D model. In this case, it's being displayed in R format, the 3D mesh, and it has built-in levels of details, pyramids. Everything is optimized for it to be able to be streamed and visualized also over the internet or in really any software. You can see over here the level of detail that the features have in terms of thin features, small statues, pirouettes, or just general areas that are pretty difficult to model. And with the combination of the LiDAR, we can also see the quality of the trees is much better, the density of the vegetation from the LiDAR correlation, as well as sidewalk data or information, which is from the top view obstructed by the trees. With the LiDAR penetration, you're able to get a lot of information underneath that and really get a complete view, especially in urban areas and dense areas where there's a lot of buildings that are close together and tight vegetation. In open areas, you'll be able to see without buildings that the vegetation really is able to get down to the ground below the LiDAR. And that's part of the advantages of having the combination. This is a good example over here. So this is the complete project. Now, there's always a question of, is it 100% necessary to control the data from the LiDAR or the imagery? In some cases, if the LiDAR had control and was able to use the same controls as the images, if essentially they're both referenced to the same survey model, then it's not 100% necessary to have control. This is an example of a project where no control was used. You can see there's 0 control points in this project. The AT of the images was done with very minimal shifting because the data was already pretty accurate to begin with. You see the mean median error is actually pretty similar to the other project, about 0.28, so also very good. And you can see over here, the images in this case did not go through any calibration. They're already pre-calibrated, and they were distortion free. So in this case, there was no need to calculate any radial distortion or shift the principal point from the original to the calculated. It was just used as the pre-calibrated data was input. And you can see over here in the AT parameters, it was using original. So use original for the focal length, the principal point. It just did a very minor shift to maybe the position and the orientation, the omega phi kappa. And you could also see in the report, there's no control. So there's no reporting back on the accuracy, but that's because the data and the LiDAR were already pretty well configured. And we can load one of the LiDAR data sets and compare. And then you could see that when we look at one of the image point clouds from the data set and the LiDAR, they line up very well. So this is a good example, and this credit goes to our partner in France, IGO, in the city of Lyon. So this is the dense point cloud. This was collected with slightly better overlap, and the LiDAR is also denser. This was probably close to 40 or 50 points per square meter. So the lines were closer together. The flight was a little bit lower, so it's a smaller area, much smaller area. The total project was about 1,250 images as opposed to 9,000 images. But it produced slightly better quality, if only for the fact that the LiDAR was denser and the image overlap was denser. So you could see areas that have tree vegetation because of the density of the LiDAR actually completely correlate the data below the trees and the vegetation. And you can see also the level of detail on vertical features because of the density of the LiDAR, gets contributed a lot. So even a thin feature like this on this vertical wall is able to be correlated very well, very high quality. So that's one of the examples of a different data set that both didn't need control and was able to utilize the denser LiDAR and get sharper features or smaller features on this type of data set. So just to address some questions as they're coming in, the system that was used for the London data was the Leica City Mapper. And the other question is, was the LiDAR collected simultaneously with the optical from the same platform? So for the London data, it was collected together at the same time. The Leica City Mapper has a combination of an image sensor, five cameras, and a LiDAR. In this case, they were not. The LiDAR and the imagery were collected separately, but they were both controlled to the same survey grade, the same survey system, the same survey network. And that's why they did not require to be controlled in PhotoMesh. They were just able to be integrated straight off the bat. And we can see here the level of features in stairs or very thin data. This is a very ancient Roman amphitheater. So some of the other questions, was anything done to the point cloud before the use in PM? So no, the answer is that there was not. We bring in the LiDAR as is. If the there's some recommendation, if the LiDAR is able to be cleaned up prior to being brought into PhotoMesh, it will perform better. If the LiDAR is very noisy and has issues in it, some of those issues might translate into the final mesh model. We do cleanup and noise removal as part of the meshing process, and some of that will remove noise from the point cloud, but generally, the better the point cloud data on the input, the better it is for also the output. The other advantage of having a denser LiDAR, like in this case, is that LiDAR only needs a single point to be able to map out alleyways or very tight areas. And in this case, we see the very thin alleys fully represented in the data set as a result of the dense LiDAR's contribution to these areas. Some other questions, if LiDAR classification is used, will the information in the class be used? Not in this version, but it's something that we're working on, and we already have some of classification visualization capabilities and visibility options in Terra Explore, our visualization tools, and we're working on integrating some of those capabilities into PhotoMesh in next releases. One thing that could definitely be done in an external tool if classification gets used is you could remove the classes that are not necessary. Like if you classify low vegetation or cars, things that are close to the ground and might produce noise on the road, then those classes could be removed from the LiDAR files and then imported into PhotoMesh without those points. So they wouldn't contribute to the mesh, and you can get cleaner roads or cleaner areas close to the ground, which is a lot of requirements for departments of transportations or civil engineering firms that are looking to get very clean data sets on the road. So these are some of the examples of thin pirouettes or flying buttresses that you have typically in Europe. Other than that, here's the example of the density of the LiDAR contributing in difficult features that have sort of holes in them or are very thin and are able to get in between to the rooftop around them or through a very thin feature like a cross on top of a church. So these are the two separate examples that we were showing. To address some other examples, other questions. For the London example, Do you know if the AT was used in HexMap or only the AT and PM? So only the AT and PM was used. The exterior orientation and the airborne GPS information was provided directly from the system, and the AT was used only in PhotoMesh. So PhotoMesh has a very robust aerial triangulation, and it does an extremely good job of combining oblique images and nadir images. And we also have the ability to run in any coordinate system for the AT. For very large oblique projects, we also have the option to run an ECEF, which is Earth-centric, Earth-fixed, which I believe that's how the London project was processed. So that also is able to have pure Euclidean geometry for the image angles and the obliques if they're higher up in the air. See, the coordinate system for the AT here was Earth-centric, Earth-fixed. So we're able to get very good correlation and geometry between the oblique images and the nadir images, despite the fact that their perspective is different and they might have been collected in slightly different times. Some other questions: how do you visualize the mesh under the trees when there is no imagery? So that's a good question. A lot of times there is imagery, but there's only a single image that points underneath the tree. And you can texture with a single image. You can't correlate data with a single image, but you can texture with a single image. So this is a good example. So you see, it's being textured underneath the tree, even though if you try to visualize an image from this perspective, it might not see much underneath the tree. You might only have one image. So we calculate the normals of the LiDAR, and you could also import trajectory information into the LiDAR, which is the trajectory of the flight. And then the points for the LiDAR receive a trajectory information, so they know which angle they were captured from. And we do a very smart extrapolation of texture. So if you zoom in, you can see what it looks like. It looks like this, but that's because there really isn't a perfect texture because no image hits that spot. But from a good perspective, you can see it blends in very well and doesn't draw too much attention to it. So it still creates a very visually appealing texture to the mesh. It's not just sort of a gray blob or just sort of a black no texture area. So that's how our smart texturing algorithm is able to utilize LiDAR points even in areas. And this is a good example where even extrapolation wasn't needed. Just the image texture was enough, and the LiDAR points to produce the whole data underneath the tree, or just a very detailed trunk, like in this case. Some other questions: how do you, what takes precedence, LiDAR or photogrammetry? That's a good question. So some of it depends on the density of the LiDAR versus the image point cloud. If the LiDAR is dense, then it's gonna dominate the imagery more. If the LiDAR is rather sparse, like let's say 2, 3, 4 points per square meter, it's hard for it to take precedence. We do give a little bit more weight to the LiDAR points under the assumption that the LiDAR points are more accurate because they come from a ranger, a ranging sensor, as opposed to an image correlation process, which has a little bit more leeway on the location of the point. So the LiDAR does get more weight in the process, but some of the process does rely on having good LiDAR density. And that's why I say the rule of thumb is that for an image resolution of about 5 centimeters, we correlate on average a point every 2 pixels. So that means you correlate, a point every 10 centimeters, even though it's not 100%. So you could get on a 5 centimeter data set somewhere in the range of 100 points per square meter. The LiDAR should be no less than about a quarter of that. So for 5 centimeter resolution, you want LiDAR that's at least 25, 30 points per square meter to have proper influence and be able to contribute to the quality and accuracy of the model. So that's relative. If you go to, let's say, 7.5 centimeter data, the number of points that will correlate from the images are closer to about 40 points. So you could use LiDAR that's about 10 points density, preferably a little bit higher. But below that, the LiDAR might contribute a little bit in being able to correlate in tight areas or below trees, but it's not going to contribute to the quality of and the precision and the sharpness of the model that much, only a little bit. Other questions, could you recommend to use UAVs equipped with LiDAR sensor? The answer is yes. We processed several data sets and we work with companies that collect LiDAR from UAV for roof inspection or for other type of infrastructure mapping where it's required to get very high density LiDAR. It is a little bit more complicated to fly with the UAV and LiDAR because LiDAR requires some higher grade IMUs and more accurate flight data, which in a lot of cases UAVs don't perfectly support. So, but we do recommend that if it's required for like bridge inspection or power line inspection, flying with the UAV with LiDAR can produce very good results, very high resolution images and very high density LiDAR. Obviously for smaller areas, but still can produce very nice models. So that is something we can address. So unless there are any more questions, I hope that this was a beneficial webinar for you and you're able to see some of the PhotoMesh tools and all the capabilities that are available for integrating imagery and LiDAR together. And please address any questions that you may have to the Skyline team, and you can always go to our website. And we have a lot of tutorials. You could reach them from our website or which directs you to our YouTube page, and they're also directly on our website. And we also have a lot of available resources to download, such as our user guide, some quick getting started tutorial, and some other sample data sets that you could work with that we can provide you. So if anybody needs an evaluation, just contact us and we'll get back to you right away. And you can also answer any questions you may have. You can just file a question on our support page on our website and we'll get back to you right away.
Thank you so much, Itai. That was incredibly informative. Everyone will receive a link of the video of today's webinar, and there will be links in that email to our YouTube page, social media, and our website. So thank you so much for joining us today, and stay safe, everyone. Thank you.
Thank you. Bye-bye.